In this series of videos, we are going to talk about the importance of clustering and the k-means algorithm for finding clusters of similar data. Now, as we've seen from our previous lesson, it is often really useful to place a collection of objects or a corpus into these smaller bins that we hope are of a somewhat similar nature. We saw this first in the context of KD trees as a way of being much more time efficient with our computations. But this is a thing that we do in other settings as well, all across the big data movement. When you're talking about taking movies and grouping them maybe by genre, or taking articles and trying to parse through that text and determine the main subject of that article in order to recommend further reading. If you're talking about looking at a collection of comments, like the FCC comments, one of the greatest analyses I've seen has gone through the comments and put them into these clusters according to what the main content of their concern was in order to parse through that very large data set. You could imagine that same thing happening. You had a congressional representative who was seeking input from their constituents on an important issue. They may want to just get an idea of what the main topics are, the big things that people care about as they're writing in to that representative. You can get even more abstract when you think about product services like Stitch Fix, where you go online and you select things you like and things you don't like, and the computer tries to learn the type of clothing that appeals to you that you might want to purchase from the company. All of these are different mechanisms by which we might want to employ clustering, where we take a huge collection of objects and put them into these bins according to things that might be of a similar style or nature or sentiment. And as you can see from this variety of examples, there are times when we might not actually even be able to describe what the bins are that are holding the objects. So for example, with something like comments to the FCC, we might not know how many bins there are. It might be more complicated than just in favor or opposed. When we get down to it, there might be different sentiments as to why we are in favor or opposed, and we might not know that until we look at the data. Or something like Stitch Fix. We might not have a word for what it is that captures our attention and our style, but we still want to put things into that bin of things that are my style and things that are not my style. When we don't know the names of the categories that we're trying to use for our clustering mechanism, this is sometimes called an unsupervised learning task. Now, the mechanism we're going to be employing for finding clusters is going to be called a k-means algorithm. And so I'd like to show you first what that algorithm is about with a visual. So I've got a picture of some data that's just plotted here on this unit square for us to consider. And these photos come through a nice tutorial that await you at this website. But here's a picture of some data, and we can see that this data is clustered into groups of things that we might find to be similar. If you think about the process that we were employing with KD trees, it was somewhat arbitrary in always wanting to half everything. So if we, for example, tried to use 4 bins via a KD tree on this type of data set, we would be splitting first according to the X median, and then on each side splitting according to the Y median and putting this data into 4 bins. And you can see that that doesn't really capture what we have going on here. It's a way of assigning bins and putting an equal number of things into each bin, but it doesn't necessarily fit all different types of data. And so what we want to ask is if there's a different algorithm that can group things a little more flexibly and a little more accordingly. So what we're going to do for k-means is we're going to first assume that we know how many bins or clusters we want. And for this example, we can see that we want 5 of them. So what we're going to do to start off the algorithm is pick 5 points at random that land into our corpus. So you can see those 5 points in red right here. From there, we're going to divvy up our sample space into 5 different collections of data, where a point in the plane is attributed to one of these 5 random theoretical cluster centers that we've created according to which one it's the closest to. So the lines that you see in this picture right here are designating the cutoffs between which points are closest to which of these 5 randomly assigned center values. Now, once we've done that, we're going to do a different process, which is to move and refine our initial random guess as to where these centers are. Now that we've taken all of the data and broken them up into these 5 units, for each one of these 5 shapes, we could compute the center of that collection of data points, or the centroid of the data points, if you'd like. And so from these 5 regions, we figure out where the center of each of those 5 regions ought to be located. And center not geometrically, but center in terms of the weight that's coming from each of these data points, which we'll describe further later. And so that's the next step of our algorithm, is replace the old random guesses with these new better guesses according to how we partitioned up the data. And then what we do is we repeat that over and over and over again, continuing to refine our guess at each stage. And in pictures, the algorithm looks like so. Now we have these new data points, and I've color-coded them. These new guesses as to what the centers ought to be for our different clusters. I break up my space according to which of my data points goes to which of those 5 centers. And of all of those data points, I take a very large average and determine where the center of that new shape really ought to be. And then for each of these centers, I'm going to move them to where that new location ought to be and start the process over. Now the plane is divided differently. There are 5 different regions, each of whom is a little bit closer to this data point, but I may still need to move my centers a bit further to balance the changing of the attribution of points. So I make those moves and I continue to reassign the data, recalculate the center, reassign the data, recalculate the center, and I keep doing that until we start noticing the absence of these little tick marks and the data points just move closer and closer to where they ought to be until they finally settle down and stop moving. And you can see that for this example, starting with just 5 random points in the plane, I was able to get those 5 clusters as I visually see them.